Okay, our next talk is going to be from Daniel Krolikowski from the University of Arizona. Forward reversing.
Cool. Awesome. Everyone can hear me? Great. Thanks. Yeah, I'm Daniel Krolikowski. I'm a postdoc at the University of Arizona. And we've had some kind of wonderful motivation already throughout this week. A couple days ago, Jesse gave a talk and really provided some motivation why we care about planets across time, the power that young planets can have in testing theories of formation and evolution. And of course, yesterday we had a great overview from Elizabeth about some of the difficulties in observing young stars and characterizing their planets. And then today we've had some kind of deeper dives into how stellar activity can affect atmospheric measurements. And kind of along that avenue, I'm going to be talking about some work that I've done regarding the helium triplet, which is an important probe of atmospheric mass loss, and in particular, how stellar activity can drive variability that would potentially preclude our ability to detect atmospheric mass loss at young ages. So when I say detecting in exosphere, what do I mean? So I just mean that we're doing transit spectroscopy to detect atmospheric mass loss. So if you have a planet that has an evaporating atmosphere, as it passes in front of its host star, that cloud of material will imprint a spectral signature. So this was first done for detecting hydrogen exospheres in Lyman alpha. But Lyman alpha provides some difficulties in observations. You need space-based observations, and there's quite a bit contamination from geocoronal radiation, interstellar absorption. And so thankfully, in the last maybe 7 or 8 years, there's been a very prolific new probe of atmospheric mass loss, the helium 10e30 angstrom triplet. And so here I show an example of its detection. Here's the helium feature. Black is out of transit, that's the intrinsic stellar line. And then red is in transit, where you can see excess absorption from the helium that is evaporating off of the exoplanet. And so this has become a really popular probe because of its accessibility. It's quite accessible from the ground from a host of instruments, including high-resolution near-infrared spectrometers, and it doesn't have the same level of contamination issues that Lyman alpha has. It has its own issues, which I'll get to later on in the talk, though. So just kind of to ground ourselves first, we can go back to some atomic physics, or as much atomic physics as I know still, to consider how this spectral feature forms, which is important to know about for considering its stellar activity effects. So you start with a neutral helium atom, you can photoionize it, and then it can recombine with a free electron, and instead of falling back to that fundamental ground state, it actually can quite efficiently populate this triplet ground state. And what's important is that this state is metastable, so the helium atom will sit there for a while, making it really a ripe target for absorption. And so it can absorb a photon at 10e30 angstroms, creating this helium triplet feature. Kind of this process is what we would call photoionization recombination, or you can directly populate this triplet ground state through collisions of helium atoms with electrons. In stars, these methods both work. You might have back radiation from EUV coronal radiation incident on chromospheric helium, or you can have collisions of helium in dense chromospheres if it's dense enough. But now, of course, I've mentioned corona and I've mentioned chromosphere. So this brings us to the one kind of biggest difficulty with this line is that it is highly sensitive to stellar activity. We see on the sun that this feature is enhanced in absorption in active regions and by flares, so it's clearly responding to stellar activity. There's been some wonderful work. This is from the Carmenes team looking at how variable this feature is in M dwarfs, and you can see as you go to the active late type M dwarfs, the variability increases a lot, actually to the point where sometimes the line is in absorption, sometimes it's in emission. It's very messy. And then, of course, the atmospheric mass loss itself is not independent of the stellar activity, right? More activity, you have more of this high energy radiative output that could drive more mass loss and also would affect the helium population in the evaporating planet's atmosphere, which would determine whether or not we could actually detect it. So all in all, there's really some significant interplay of stellar activity and exospheres that could cause some confusion, right? If the stellar line is responding to things that are happening on the star, you could mask or mimic an exosphere detection. And so we really need to understand how this feature responds to stellar activity, particularly for young stars. So what have we done? So we have collected a very long monitoring campaign of a collection of 24 young transiting planet hosts with the habitable zone planet finder in McDonald's Observatory. And so we've been observing these stars since it was commissioned about 8 years ago. And so we have very long baseline for these observations with which we can look for variability in the near-infrared spectra. Even though we've been observing for years, we have cadences of observations on the order of days, weeks, months, so we can really tease out some of the timescales of this stellar variability. Primarily, this was originally an RV survey, but we get helium for free, so it's worked out really nicely. And I do note we're using only a subsample. We're throwing out all the M dwarfs that we've observed because I don't touch that. That's a little too much. So before we dive into the helium variability itself, I want to highlight the other big difficulty with observing it. And that's kind of what I would say is, know thy star, know thy planet also does mean for some of these observations, you need to know thy sun and know thy earth, to know thy star and know thy planet. And what do I mean? If we take a look at the spectral region around helium, it's a complete mess. So there is the stellar helium feature. I guess you can see it, but it's being swamped out by telluric features. There's a really strong sky emission line and a strong water absorption line that, depending on the velocity between us and the target, can directly overlap helium. And so correcting for that is very important if you want to precisely measure helium absorption strength. So I'm just going to say, trust me that we can remove that quite well. I've done a lot of work on this. Find me later if you have any questions. But here's our nice spectrum. You can do a spectral fit. And then for all of our targets, we now have time series spanning years of helium absorption strength for these young stars. So there's a lot you can learn about the star itself from this, chromospheric structure, things like that. But I'm going to just focus on the variability since that's kind of what's most important for detecting exospheres. And so just to start, we'll kind of go at the most basic level. What are typical variability amplitudes for these young stars in the stellar absorption strength in the helium feature? And so here, what I have plotted is, after kind of deconvolving measurement error, the variability in the helium equivalent width or absorption strength as a function of age. And it's not surprising. At the youngest ages, the feature is very, very variable. It drops fairly expeditiously, about half by 100 million years. And then actually, at the kind of intermediate ages, 300 million years and above, it plateaus and is in line with the field. And so this is really due to the evolution of activity at these young ages. You have the most flaring, most rapidly changing surface heterogeneities, and that's what's driving the variability in the helium feature. But it's promising that at these kind of intermediate ages, if it's in line with the field, then you might not be any worse off detecting a young exosphere than from a field age exosphere. But transits are inherently temporal observations. We don't just care about the amplitude of this variability, we care about the time scales of the variability. So what we can do is, for all of our time series, we can measure the kind of pairwise difference in helium absorption strength as a function of the separation of the observations. So that's what I have plotted here. In red, for the youngest star in our sample, V1298 tau, at about 25 million years. And then in blue is all of the other stars that are 100 million years or older. And you can see that at the shortest timescales, below a few hours, the variability amplitude is actually independent of age. So that's great. So on timescales that are relevant for transits, the variability might not even be worse off at these youngest ages. But then you can see that beyond a few hours up to a day, the youngest stars, the variability starts to really explode. Although at these intermediate ages, it's still okay. And we might be kind of benefits of long baselines, picking up activity cycles or something. But so this is good. But to kind of key in on this youngest star, we can use that as a case study of what does this variability actually look like in kind of temporal morphology. And thankfully, we have an intensive campaign of this star where we observed it once or twice nightly for about a month. And we can look at the helium time series for that. And it's quite a bit of a mess. So you can see in the first week and a half of this campaign, the helium line is varying wildly by up to 50%. And then the rest of the campaign, it's still variable, but a bit steadier. And kind of interestingly, in this first week and a half, it has power at the rotation period of the star, but then there's no power at the rotation period in the rest of the campaign. So if you phase fold it up, in that first week and a half, you can see there's a sinusoidal signal, the rest of the time not. So something is going on, some sort of massive hotspot, a mass loss event that fell back down, that's causing rotational modulation for some time, but then all of a sudden it turns off. And actually, you don't see any rotation signal for the rest of the stars in our sample. So it seems like, whereas on the sun, we can see that the helium feature varies as surface heterogeneities come in and out of view. For these young stars, the variability might be dominated by more stochastic events, flaring, or just general activity in the chromospheric network. Now, of course, the main question is, will this preclude young exosphere detection? And so that requires us to compare these variability levels to that of exosphere signals. So what I have plotted here is a collection of detections and upper limits for helium exospheres in terms of their excess absorption depth percentage. And so we can take those initial kind of time-averaged helium variability amplitudes for the young stars, convert that to an equivalent depth variability that is more or less comparable to an exosphere excess absorption depth measurement. And so if we plot that on here, these horizontal lines, at the youngest ages, 25 and 100 million years, you can see that this variability amplitude is actually larger than most of the known helium exosphere detections or upper limits. So that's kind of concerning. But by kind of 300 million years, they're comparable, so that's good. And of course, this is that long-term time average typical variability. We already saw that on the shortest time scales, like that of a transit, the variability is smaller. So I think it's promising that for contemporaneous out-of-transit baselines, you should be able to better remove the variability contamination. Now, that's not to say that there certainly are complications that can occur. Observations aren't always perfect. There's weather, there's reasons why, transit timing. You might need to compare your transit observations to comparison spectra further away in time. That'll increase the chance of acute activity events like flares, causing difficult to remove contamination. There's a host of extended exosphere structures we've seen. Jessica Libby Roberts showed one earlier this week, and so that's going to increase the chance of these acute activity events. And then, of course, this lack of rotational modulation might make it a little difficult to model out the signal and separate the stellar and planetary signals. So with that, I'll just leave up my conclusions. I have a QR code there for the paper if you would like to read more, and I'm happy to take any questions.
Okay, we have a question for Danny up there.
Hi. As Annabella talked about this morning, high-res observations have the advantage that we can do velocity resolution between the star and the planet. Are you able to use that at all to even just merely mask out the stellar activity? Does that work in some cases, not at all?
Yeah, I think that's difficult. I'm trying to remember if there's really been much in the way of kind of like velocity resolution of the helium absorption. I don't think so. I think that'd be quite tough to do. Because you have this kind of broader excess absorption happening. I think it's certainly something that could be done if you have high enough signal, but I don't know if we're there yet. And then the other sources of contamination, the telluric contamination, things like that, can very easily kind of mask out potential velocity signals and really drown out anything in systematics.
Thanks.
Okay, down here in the front.
Dan Huber, Hawaii. Nice talk. You do have the ages for some of the stars we've detected exospheres, presumably. So can you give us, not to put you on the spot, but can you give us an estimate of how many of these detections might actually be due to stellar variability if you divide them into young ones and old ones that are less affected?
Yeah, so I might be a little out of date on the literature, but most of the young planets that have been targeted for exospheres have just turned up upper limits, which is maybe already surprising. You might expect them to have more mass loss. Something might be going on with the helium populations in atmospheres there. There are at least a couple of robust detections, or at least one robust detection, kind of in that intermediate age range of like 400 million years. So I don't think so, but I mean, you can see V1298 tau, there have been searches for exospheres there, and I mean, there's some tentative detections, but you can see like slopes in the helium strength and things that are definitely stellar variability, but I mean, those haven't been claimed to be exosphere detections, so.
Okay, let's thank Danny again.